All right, so here we are. This is physics reaction video number 38. Checking my little list there. And this is an exciting one because I did start the new project where I'm encouraging people to go ahead and suggest themselves or one of their videos to watch. And the idea is that I will try to do a few of those in a week and then maybe contact those people and see if we can get together and do just a fun debrief of what we've learned from each other and just ideas about teaching physics. So this is someone who submitted themselves, and off we go. I haven't watched this video, which is my usual story here. And as usual, here when I'm working at home, I'll have to move my face all around. Sorry about that.
Right, okay, so that was 69. We'll have go now at number 70. All right, so again, I'm going to start with a little diagram as I read through what the question is asking me. So a soft ball, and we'll see why that's relevant.
I really liked what she just said. You probably saw me, I was leaning in trying to read the problem, but then she said something really, really awesome. She said, I'm going to draw a figure as I read. So it's probably not going to be the greatest drawing. I don't know, maybe she's prepped for this, I'm not sure, but it's modeling for her students how to read the problem, right? Like you should have your pencil out with some paper out, even while you read, because every single thing in there, well, I was going to say is useful. I guess more likely to say is potentially useful. And if we can get it into a different representation, we already have one. We already have the text, but you can make your own representation with a drawing. So I'm just going to back her up and listen to that again.
And I'm going to start with a little diagram as I read through what the question is asking me. So a soft ball, and we'll see why that's relevant in a moment. We'll call A, of mass 500 grams. So I'm going to read.
So sorry to laugh, but it's interesting there that I think of it as softball the sport, which would normally be one word. As you can see, this is two words here. So I was thinking this is just a throwaway line, like it's a softball or a baseball or a tennis ball or a golf ball. But because it's two different words, and did you hear her emphasis? She said a soft ball, she says is going to be important. And I'm trying to keep myself from reading the rest of the problem. But right away, every single word she says might be important. So let's see what we're going to do.
I'm immediately going to convert that into kilograms. Moves to the right.
Immediate conversion.
With a speed of 3 meters per second. And it collides with another softball, B, that we don't know anything about, except that it was moving that way. Okay, so we don't know anything about B. Right, so that's my before scenario.
So I just want to talk a little bit more about cultural experience. So again, because my brain went to the sport, softball, even though it's written as two words, right? My brain, you heard, you witnessed it. I literally thought it was about the sport. And what's interesting about that is that if I were to continue that assumption, I would assume that ball B is also 500 grams. So let me think, 500 grams, half a kilogram, so a pound. So 8 ounces of water, I think, or maybe that's 16 ounces of water. So yeah, I think that's heavier than a softball. So I don't think this is the sport. But she's saying, look, they didn't tell us anything about how much it is. The other thing that I'll point out, and I've seen this every once in a while, is this meter second inverse, right? I think that my standard would be to do meters per second with a little slash. But she's following, obviously this is the textbook they're using. So the textbook clearly writes it that way. And I did react to another video that was saying something along the lines of, this is how we do it, or this is how the exam is going to do it, or something like that. So I do believe that there's maybe a curriculum out there or a textbook out there that really kind of drives this home. What's interesting about it is that when you write things like this, let's say you have a big, ugly, gross one, right? Like writing joules out as, kilogram, meters, square, seconds, inverse 2. It's all on one line. You can see it all there. They're all getting the same amount of emphasis, I guess. And then the negative is very clear that there's something interesting about it. It means it's in the denominator. So I'm intrigued what you guys think about this. I would say that I guess it's a bias would be to use the slash or truly use for like fractions. But I'd love to hear a little bit more about the value of this, because I think I could see it in how it keeps the emphasis equally on every unit. So I'm just going to go back a second.
Okay, so we don't know anything about B. Right, so that's my before scenario. So they collide. They collide, and we've got a time of impact. And then we've got an...
That was cool. Possibly rehearsed, but it sounded supernatural. Did you hear her? She's like, oh, wait a second here. There's something interesting going on. So, I think that physics teachers were like, oh yeah, ball, okay, moving, yep, another ball, okay, yep, okay. And I think that I was just assuming that this was going to be, and afterwards it was doing something, which we have, after which the ball, blah, blah, blah. But there's this fascinating extra piece of information that you would only be able to get with maybe high-speed video or super fancy detectors in the balls. But we have it. They're giving it to us. And so you heard her excitement or maybe surprise that information was given. And I guess I should have guessed it. Look at the name of her video, right? It's an impulse example. So if we didn't have this information, all we would be able to calculate is the total impulse. But with this, I would imagine we're going to able to, well, I'm trying not to read the rest of the problem, but we can make assumptions like the force is constant during that 0.34 seconds. We could try to figure out the G forces, the average G forces. Like, are these balls going to be destroyed? Okay, let's keep going.
Got an after scenario. So my after scenario, again,
Love
we
it.
don't know anything about B. But
Love it.
we do know that A now still has the same mass, but now it's moving, it's rebounded, it's going backwards at 2 meters per second. So in other words, the velocity now is -2 compared to what it was before.
Love that.
And the
Love
bit of
that.
time, so before this, we know that this collision took some time, and the time taken, in other words, delta t for the collision is 0.34 seconds. All right, so that's
Cool.
all the information we've got.
So I'm thinking if let's see. So she said something that was super, super useful. She said it still weighs the same. Its mass is still the same. So the mass of part A, it doesn't actually say that. But it's still calling it the ball A. So maybe we assume the mass is the same. So I'm trying to think here. I believe that means immediately that this is an elastic collision, because that would mean that B still has the same mass. But I guess it doesn't have to be an elastic collision because it could get deformed, right? So the ball could come back having the same mass, but some weirdo, some parts of it bruised or crushed or something. So I guess we don't absolutely know that it's an elastic collision, but I'm guessing we're going to assume it is. Because we literally don't have enough information otherwise. Because we'd either have to know the force during that 0.34 seconds, or we'd have to know something about particle B, the ball B. And since we don't, I believe we have to assume this is an elastic collision. Let's see how she deals with that. Just back her up a little bit.
Seconds. All right, so that's all the information we've got. So let's go through these. First one, nice and easy. What's the change in velocity of ball A? Well, it was going 3 meters per second that way, and now it's going 2 meters per second that way.
So I'm just going to pause her right there, because what I have found is that if I ask students to give me the answer without writing anything down, a lot of them will get to 5 pretty quickly. But some will say 1. Some will say, well, 3 minus 2 is 1. But what's interesting is my guess is she's about to write -2 minus 3 will give a -5 of a change of -5, because that's what it's asking for. And students sometimes get really fouled up by the negative sign. So I do like to start by sort of looking at this diagram here to say, come on, guys, is this a big change or a small change? And say, well, 3 became 2. It's a pretty small change. So, well, hang on. You had to turn it all the way around and then gain an extra 2 going back the other way, right? So I like to motivate what the answer is before possibly getting stuck in some sign errors. So I'm curious if I think she's going to write -2 minus 3 equals -5. But let's see if she puts any parentheses in there or if she emphasizes any of that. Go back just a little bit.
Meters per second that way, and now it's going 2 meters per second that way, that's a total change in 3 minus -2, which is 5 meters per second.
Okay.
Is the change in the velocity for that. So what's the change in momentum?
So that's interesting, because if she had said at the end, to the left, then it would be a magnitude and direction change. But it's beautiful, right? Because clearly the direction is embedded in this diagram. There is no way students don't understand what the change was. And then this 3 minus a -2 works out fine. I was thinking it was going to be -2 minus 3, final minus initial. But obviously it works either way. And wonderfully, she got a nice positive result here. And of course, the magnitude is embedded, the direction is embedded in her diagram. But I do wonder about, boy, anytime you do change, you have to do minus initial, right? Like, how much are her students going to be thrown by that? How much is that going to be a problem moving forward in this problem? The story is there. Would I take points off for that? I don't think I would.
Momentum. So change in momentum is, I remember I said it could be a change in mass or a change in velocity. This time it's definitely a change in velocity. So we're just going to do its mass, which was 0.5, times that change in velocity that we just calculated. Is 5, gives you a change in velocity of 2.5. I'm going to stick with newtons per second just because it's shorter. Right, nice and easy so far.
Love that. Newton seconds.
It's asking you for, what's the average force?
By the way, Newton seconds for momentum. I pick on the units of momentum all the time. It's such an important concept, and yet we've never given it a unit. And I was reviewing somebody who gave it whatever his last name was. I can't remember. I think it was single syllable last name, and I just thought that was great. I've given it POMS, P-O-M, as the unit of momentum before, just when I'm joking around with my students. But what's fabulous about Newton seconds is that it totally makes clear how changes in momentum can come to be. So a force applied over some time. Right? Newton seconds. So I sort of like that. It sort of drives that home.
C is asking you for, what's the average force? So the average force exerted. Now, this won't be a constant force. If there's two balls colliding, they're going to squidge a little bit. They're soft balls. So it's going to squidge the balls together a bit. So that force is lasting over 0.34 seconds. So it's going to be an average force that we're calculating. Is, if you remember from Newton's law, it's the rate of change of momentum. Newton's second law. So that's the change in momentum, 2.5, divided by the time, 0.34 for that collision. And that gets me that the average force was 7.4, I'm rounding, newtons for that collision.
So again, here the units work out really beautifully because it's Newton seconds here and seconds here. It's obviously newtons, right? So again, this way of using Newton seconds for momentum is super interesting. So again, we have the same sign propagation, right? So if you're going to call this positive, you're going to call this positive, you're going to call this positive. Every single one of those is to the left, right? And that's super, super obvious, again, from the drawing and from the initial setup. So you don't really need to hammer it home. And what I love about positive numbers here is it really helps students focus on, wow, is that a lot of force? Is that not much force? So 7.4 newtons is what it would take to lift something less than a kilogram off the ground, right? Because if it's 1 kilogram, it would take you 10 newtons. Yeah. So I'm trying to think of something around me that's less than a kilogram. Well, my phone's too light. Keyboard's too light. My whole laptop is a little heavy, right? So that amount of force over 0.34 seconds doesn't seem like it would damage a ball. So I don't think we're going to get much inelasticity going on here.
Right. That's all the calculation bit done. What I'm going to do now is look at these ones over here.
Cool.
So D, E, and F are asking you to sketch a force time graph. Now, don't be fooled by the word sketch. This is IB. They've given you numbers. That means you need to use the numbers. So,
oh my gosh, that was so fantastic. So What she said was, don't be fooled by the word sketch. You have numbers. You can't just willy-nilly draw something. And I remember I was teaching some teachers, actually. So these were some chemistry and biology teachers who were trying to get their physics license in the state of Minnesota. So we had this super cool program. We ran it for 5 or 6 years, and I think we licensed like 80 physics teachers. It's Minnesota is still ranked high for how many licensed physics teachers we produced from that program, which is now 5 years old. That's when we ended it. Anyways, there was a day when we were in lab, and I said, well, why don't we estimate estimate the something force. And I think what I meant by that was to make reasonable assumptions about the time the impact happened, reasonable assumptions about this, that, and the other thing, and give me an estimate. But they were like, done. Can you come over here and take a look? I was like, wow, okay, what do you have? And I mean, they were just wild, crazy answers. And I was like, well, how did you get to that? They said, well, it said estimate. And they were interpreting that to mean guess, right? Like just whatever, 143,000. And so I was like, oh, I need a different verb. And I don't actually remember what verb I ended up using that day. But here, I loved what she just did, right? It says sketch. That sounds loosey-goosey. But it's not, right? There's some serious numbers you have to use. So I love that. Let's go back a tiny little bit.
They've given you numbers. That means you need to use the numbers. So we need a force time graph. I'll just get some axes. Force on the y-axis.
We should do constant.
Time on the x-axis. Right, so for that impact, what do we know? Well, we know that the whole thing, so we need to put labels on this, the whole thing took 0.34 seconds.
Cool.
Okay, we've calculated an average force. That means that that wasn't constant, and there must have been times where the force was bigger than that and times where the force was smaller than that. We're going to assume, just to make things nice and easy, that this collision is symmetrical. You know, they came in and then went out the same way that they'd come in. So what this is going to look like is similar to what we did in the lesson. So it's going to go up and then come back down. Probably not a spiky graph like that, because we've been told that they were soft.
Oh, I love that.
So it's one of the flatter curves. It should be vaguely symmetrical. And what do we know about this point here that is symmetrical? Well, if that's symmetrical, that's going to be
0.17.
halfway through that. So that's 0.17 seconds.
Awesome.
So label that if you know it. And at that point there, what is my force? So the average force is 7.4. So what's my maximum force? Okay, so that's F max, maximum force, is going to be double my average. Okay, so that will be...
I'm trying to think here. Does it have to be double? What we know for sure is that if we drew a horizontal line at 7.4, right, that's the area we need. And if you imagine extending this box, would this have to be double? Certainly, if it had been the very low, skinny, tall thing, it could have been super high. I actually think this is only double if this is a straight line here, because I'm just thinking about, you know, this triangle representing half the area. But the way that she drew it is close enough to a triangle that certainly the idea that the maximum force you get is twice as much, I think, you know, is more, right? In the vicinity of twice as much is super, super useful. So this ball momentarily is able to withstand a very high force. I also really, really love the symmetry that she's talking about. Imagine two balls colliding and going back out again. It would be so weird if going in, it was like smooshy, 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 and it like sprang back really fast. I don't know. I mean, we're so used to spring-based forces. We're so used to that symmetry. But obviously here is a problem. I don't even know what this is for. This looks like it was for some other, it doesn't say what problem it's for, but this is a very asymmetrical one, right? You can imagine two balls go in and then kind of stick to each other a little bit so that now when they go out, they stick, and then finally let go. That, I suppose, could be asymmetrical. So I really loved how she was focusing on that.
14.8. on there. So that's what that graph looks like. Now I'm going to change my colour of pen for E.
I was just thinking, how would you assess part D if your students turned it in? What are you looking for? Clearly symmetry, she's driving hard, that the max is higher than the average, and that the time is labeled correctly. I think that all three of those are the things I would be looking for.
Because it says, sketch a possible force time graph for a collision between two hard balls that have similar masses and velocities. So what we need to know is that it's going to be more of this shape than this shape. And on these axes I've drawn, it's also going to be a shorter, sharper collision. So the two things I need is a shorter collision time.
Love it.
Shorter collision time and a larger, a higher maximum force. So anything as long as it's a higher peak and finishes earlier. Should still look vaguely symmetrical, which mine doesn't. Okay.
So I like the self-criticism there. Should look vaguely symmetrical, which mine doesn't. I think the other thing that has to happen here, because it says at the end of E, it says similar masses and velocities. I guess I was just assuming that the area under the curve would have to be the same, right? The area under the curve represents the change in momentum. And let's see here. The question would be, does all of this area fit into all of this area? I would say she probably needs to make it a little bit taller, but close. And again, how would you assess this, right? And what would you be looking for from the students? And again, so I'm constantly talking about video as a teaching tool, but I use video as an assessment tool, right? So I want my students to give me a video back. And sometimes the drawings are crap, right? But what they say is so important. They'll say, oh, well, I should have drawn this a little bit taller, should have been a little bit more symmetric, but I really need this area here to be equal to this area here. Well, boom, I'd be like, sold, even though your drawing didn't have it. So that's really cool. Just back her up a little bit.
And finishes earlier. Should still look vaguely symmetrical, which mine doesn't. Okay. So something like that would be fine. Now, my final one, I'm just going to change colour pen again, is F.
Ooh, I love F.
Now for F, how would it look for ball B? So ball B over here we've been completely neglecting. We don't know anything about ball B. But we know that whatever A did, regardless of the mass and the velocity, the force and the time, remember Newton's third law, equal and opposite, it's got to be the opposite
Love it.
of A. So again, it doesn't matter what the mass is.
I just noticed the time running a little long here. Loved it. I really loved so much of this. I think that the way that she read the problem was fantastic, and that she was reacting to it and putting notes down. All of this diagram came out as she was reading. I was intrigued by this directionality diagram, basically holding all the directionality and then basically being magnitudes down here. But that, again, helped us sort of have a number to plot. It would have been weird over here if she had negative numbers, right, over here. So I think that that's interesting, though she gets there with this opposite down here for part F. I really like the choice of units. I'm intrigued by the inverse units, so please give me some feedback about that. And I really liked how she sort of focused on D, E, and F. There's so much physics involved there. So really great. So hopefully we can get together with some others who volunteered themselves and we can do a debrief. It might not happen for a little while, but otherwise I think this was great. And so I hope everyone has a really wonderful day. And remember, physics teachers are awesome.